Yeah, as Ed mentioned, I'm Jason Smart, Senior Director of Fire Engineering here at the American Wood Council, and thank you very much to Sandra and everyone here for the invitation. And as Ed was talking about, this presentation really focuses primarily on the FDS, on the Fire Design Specification for Wood Construction, and the way especially mass timber, because this is what we're focusing on here is the application of using the FDS towards fire design of mass timber. And the way in order to meet the requirements in the code for fire design of mass timber, I don't know how you do it other than using the FDS if you're using one of the analysis approaches for determining fire resistance ratings. Now, there's another approach which I'll get to in the course of this presentation.
Body of practice.
Can you hear me? Am I just heard someone interrupt. Okay.
You're okay, Jason. There was just
Okay,
a
great. There's another approach which relies on testing, in accordance with ASTM E119, but obviously that can't be done for every assembly and member. So anyway, um, just to give a brief outline of what we're going to cover here, I've broken this presentation into four sections. In the first section, I'll give an overview of the building code provisions related to fire safety of mass timber construction. Again, we're focusing on mass timber here. Then we'll talk about the standards and resources that are available for mass timber design in order to demonstrate compliance with the code provisions. These same resources can be used for more than just mass timber, for any kind of wood construction, of course, but we'll focus on the application towards mass timber. And then third, we'll delve into the contents of these standards, especially the FDS, and I'll explain how that can be used, how the FDS can be used for design of mass timber buildings. I don't know if we'll have enough time for the fourth section. It's part of the main webinar that we have, an hour-long webinar that we have on our website. But if we do have enough time, I'll quickly go through quickly go through the design of protection for connections, fire protection for connections. All right, so let's start with the foundation of understanding the fire safety related code requirements that apply to the new mass timber construction types in the IBC. Just to give a high-level overview of the fire safety-related building code provisions that are applicable to mass timber construction, many of the code provisions rely on AWC standards like the NDS and soon to be reliant on the FDS, especially even more so than the NDS. And also reliance on secondary references like Technical Report 10, TR10. And I'll talk about each of these through the course of this. The code provisions that I'll discuss here today are the same in both the 2024 I codes and the 2021 I codes. And these mainly pertain to fire resistance requirements, fire resistance rating requirements for building elements. And of course, I understand that the 2021 I codes form the basis for the Michigan code. So it's relevant, even though you see a picture of the cover of the 2024 I codes here on this screen, this is still relevant just the same to Michigan and the 2021 IBC. So as you probably know, the three new mass timber construction types in the I codes are types 4A, 4B, and 4C construction. And several of the key performance features that have been built into these new provisions for 4A through 4C construction are listed here on this slide. These are not all of them. This is not an exhaustive list, but I'm just going to go through some of them here. As I mentioned, every building element needs to be either mass timber or non-combustible in these three new construction types. Mass timber elements need to be protected with non-combustible protection as specified in section 602.4. For most mass timber surfaces in type 4B, all mass timber surfaces in 4A, the requirement is that 2/3 of that fire resistance needs to come from non-combustible protection. And also structural elements are required to have fire resistance ratings as shown in IBC tables 601 and 705.5. It's the greater of those two fire resistance ratings that applies. The adhesives that are used in CLT are required to be qualified through a series of both small scale and large scale fire tests. And this is to ensure that they do not undergo heat delamination during a fire that could lead to fire regrowth rather than continual cooling. And no combustibles are allowed in the concealed spaces except for those materials which are currently allowed in plenums by the IMC, International Mechanical Code. In types 4A and 4B construction, one other requirement is that mass timber floors are required to have a minimum 1-inch thick non-combustible material above the mass timber. And then in all three of these new construction types, everything outboard or to the exterior of the mass timber in exterior walls is required to be non-combustible. So, except for the water resistant barrier, and that's required to meet other fire performance thresholds. Also, there's a requirement for the exterior mass timber walls to have at least 40 minutes worth of non-combustible protection on the outside. And there are also requirements for non-combustible protection to be applied during construction, for water supply to be present also, and standpipes to be installed during construction. And the requirement for non-combustible protection during construction applies to mass timber surfaces that are more than 4 stories below the uppermost floor under construction. And then one thing I want to stress especially is that for all three of these new mass timber construction types, automatic sprinkler systems that are compliant with NFPA 13 are required. And in buildings greater than 120 feet tall, redundant water supplies are also required. And so these added levels of protection are similar to what would normally be required in other buildings that are greater than 420 feet, but they apply to mass timber structures that are greater than 120 feet. So, these go beyond the requirements for other construction types. Also, shafts are required to be constructed of non-combustible materials in buildings that are over mass timber buildings that are over 12 stories or 180 feet. But of all the fire safety requirements that we just went through, the one that I'm going to dwell on here in this presentation is the requirement for fire resistance ratings in accordance with IBC tables 601 and 705.5. So you may know this already, but I'm just going to go through this review. There are required fire resistance ratings in the building code for given building elements, and that depends primarily on the type of construction in table 601. And in the case of exterior walls, also there are requirements in table 705.5 that depend on occupancy group and fire separation distance, in addition to construction type. Table 601, which we'll concentrate on here, indicates the required fire resistance rating based on construction type. And these three new construction types are circled in red here in this table, types 4A, B, and C. So here's one of the big differences between traditional heavy timber construction, which is now called type 4HT, versus the three new mass timber construction types. And that is that the new mass timber construction types require fire resistance ratings for building elements like the primary structural frame, floor, and roofs. Whereas type 4HT doesn't have any specific fire resistance rating requirements. Instead, type 4HT building elements are required only to meet the minimum cross-sectional dimensions that are specified in table 2304.11. By the way, those same minimum dimensions apply to the elements, mass timber elements in types 4A through C as well, but they also have the minimum fire resistance rating requirements. So in this here, you can see the type 1A and type 1 or type 4A are both highlighted in red here or circled in red. And that's to point out that the minimum fire resistance rating requirements are the same for both 1A, type 1A, and type 4A. So yeah, that amounts to, let me go back to that there. That amounts to a 3-hour fire resistance rating requirement for the primary structural frame and 2-hour fire resistance rating requirement for the secondary structural members. And then likewise for both 4B and 4C, the same fire resistance rating requirements are applicable as are applied to type 1B construction. So here we have 2-hour fire resistance rating requirements across the board, except for non-bearing walls and the roof, the roof requires a 1-hour rating. Non-bearing walls don't have a minimum requirement. So despite these equivalencies to type 1 construction in terms of fire resistance ratings, the limits on heights and areas for 4A through 4B are not unlimited, as you can see, or as you probably already know. They're not shown in this table, but type 1 construction, of course, has a lot of unlimited. For most occupancies, it's unlimited heights and areas, but that's not the case for types 4A through B or A through C, 4A through 4C. So that just adds one of the several layers of fire safety that apply to mass timber in the code provisions. So the code recognizes 7 methods for establishing fire resistance, and any of these 7 methods can be applied to any construction type wherever fire resistance ratings are required. And they're all based on the same standardized fire exposure. That's what's specified in ASTM E119 or UL 263. And these include options like fire resistance designs in approved sources, calculation methods, and engineering analysis based on comparisons to tested assemblies. But as you can see from this list, a member assembly does not necessarily have to be individually tested to be recognized as having a fire resistance rating. Of the 7 recognized methods for determining a fire resistance rating, the one that I've circled or that I've highlighted in red here is the one that we're going to dwell on most today, and that's calculation of fire resistance ratings per section 722. All right, so moving on to the second section. So we just took a brief look at the fire safety related code provisions for mass timber construction, especially fire resistance ratings. And now we're gonna look at code reference standards and other design guidance that are available for the purpose of demonstrating compliance with these code requirements. Sorry about that. All right, so IBC section 722.1, which I just mentioned as one of the compliance pathways for demonstrating fire resistance ratings, references chapter 16 of the NDS, the National Design Specification for Wood Construction, for calculating fire resistance ratings of exposed wood members and decking. AWC's Technical Report 10 or TR10 provides background, empirical validation, and examples on how to perform the calculations specified within Chapter 16 of the NDS. So TR10 is somewhat like a secondary reference in the code. And then TR10 and Chapter 16 of the NDS deal with the same methodology, and it's a mechanics-based methodology, which I'm going to describe in more detail here shortly. In fact, Chapter 16 of the NDS is based on the methodology that's presented in TR10. However, TR10 goes into a lot more detail, and it actually gives examples on this methodology. So it's a great resource. And then more recently, the AWC Fire Design Specification, or FDS, has been developed to provide a lot more guidance. That's what we're going to focus primarily on here, because it really provides some of the guidance that's absolutely necessary to perform these designs. Doesn't even exist in the NDS at all. And so you really need the FDS, and that's why it's being worked into the I code starting with the 2027 version. Here's the actual code language from IBC section 722.1, which deals with calculated fire resistance. And as you can see in the highlighted text here, Chapter 16 of the NDS is referenced as the standard for calculating fire resistance of exposed wood members and wood decking. Notice it says exposed wood members. It doesn't deal with protected wood members, which the FDS does. And then, so Chapter 16 of the NDS allows fire design of exposed wood members for fire resistance ratings up to 2 hours. It applies to any exposed wood member, including those in beams, columns, wall assemblies, floor ceiling assemblies, and roof ceiling assemblies. And the materials that are addressed in Chapter 16 of the NDS include sawn lumber, glulam, structural composite lumber, and cross-laminated timber, CLT. So the more detailed provisions using the same mechanics-based model are provided in Chapter 3 of the FDS. And like the NDS, the FDS can be used for calculating fire resistance of exposed wood structural members, but the FDS provides a lot more guidance. For example, it has provisions for calculating the fire resistance of protected wood members, fire resistance rated assemblies rather than just members. It can be used for assemblies and also for fire protection of connections. And some of the guidance provided in the FDS that's not included in the NDS include in section 3.2, the FDS provides calculation procedures for determining the char depth on exposed wood members. Those are consistent with the NDS Chapter 16 provisions, but the FDS goes further because it implements new procedures that account for char penetration at intersections and abutting edges of exposed wood members. So using the char depth calculations that are determined in accordance with Section 3.2, Section 3.3 of the FDS provides calculation procedures for determining the structural fire resistance of exposed wood members. As with Section 3.2, these provisions are consistent with but more extensive than what's in the NDS. And so once the reduced section properties of the wood members are calculated using the provisions of the FDS, sections 3.2 and 3.3, the design strengths used to determine fire resistance is calculated by multiplying these reference design values, such as bending strength and tensile strength, by adjustment factors specified in Table 332, which you see here. And you can see the K factors, design member stress to strength factor. What the K factors do is adjust it to an average strength level from the allowable stress design level to the average strength level. Section 3.4 of the FDS contains new provisions for determining the protection time provided by multiple forms of protection. And these recognized forms of protection include Type X gypsum, additional wood cover, and certain types of insulation. Or you can have any combination of these as well. And so the methodology and empirical basis for these provisions are the same ones that are used to justify the non-combustible protection provisions in the IBC for mass timber. Section 3.5 of the FDS contains new provisions for calculating the structural fire resistance times of protected wood members and assemblies. Again, these provisions are consistent with code-recognized procedures for protection of mass timber elements. I wanted to point out that the FDS provides guidance for design of both combustible and non-combustible protection. So, like, for example, one example of combustible protection, the only one I can think of really right now, is wood cover, additional wood cover. And then there are multiple examples of non-combustible protection, but the most common one would be Type X gypsum panels. And then in Section 3.6 of the FDS, there are new provisions for calculating the thermal separation time provided by an assembly of wood layers or Type X gypsum protection or some combination of these, or also insulation. You can use insulation as well. So I wanted to point out that the thermal separation time is a different concept from that of protection time, which I mentioned a couple slides back. Although these same materials can be used, wood cover, Type X gypsum, and insulation, they can be used for thermal separation. The calculation procedure is different for determining thermal separation. We'll get into that in a couple slides when I go through an example or two. And then Section 3.7 of the FDS clarifies that burn-through detailing is only required where thermal separation is required. This section then references within the FDS 3.6, Section 3.6, for the purpose of thermal separation. Let me go back to that because I wanted to point out that thermal separation time it's crucial when you're designing connection protection, where you have to meet or you have to stay below a certain temperature rise threshold at the interface between the connection and the protection itself. All right, so Importantly, dealing with connection protection, that's where Section 3.10 of the FDS comes into play. And I don't know if we'll have time to get into this in much detail at the end, but if so, I can show some of the provisions there of connection protection in Section 3.10. That'll be in the fourth section. So, okay, let's move into the third section here. How am I doing on time, by the way, Sandra? I don't know. She may have stepped away.
You're good.
I stepped
Okay.
away.
Okay.
Maybe like 15 minutes or so,
Sure.
Jason.
Oh yeah, in that case, I probably
10
can get
minutes?
some of the
10?
yeah, I probably can get into at least partially into the fourth section there. All right, so in the third section, I'm going to talk about ways in which compliance with building code provisions can be demonstrated through the fire design using these standards that we just went through, the NDS, FDS, and TR10. All right, so here's FDS table 3.3.1.2 again. I showed it a few slides back, but let's focus on it more here. It provides a quick design reference for determining the char depth at a given exposure time. And those are the values that you see in the middle column of this table here. The char depths are given in inches for corresponding fire resistance rating times of 1 hour, 1.5 hours, and 2 hours. And then the column on the right provides values of effective char depth, or A effective. And notice that these values are about 20% greater than the values in the middle column. And that accounts for strength loss in the heated zone between the cool wood in the core and the char layer. And so it's used, the A effective is only used for structural fire design, not for design of protection. So for a design of protection, you'd use that middle column, HR. And then the table I showed on the last slide, that was specific to, or it was for every type of wood material except for CLT. So let's talk about the model, the char depth model for CLT now. The model was developed through an empirical process, just like the char depth model for all the other wood types or wood member types. And as you can see, it fits the empirical data fairly well. Here are the values that come from. I'm not going to show you the equation for the char depth model, at least not on this slide. I think it might be on a later slide. But these are the values, the char depth values that would come from the char depth model for CLT. And notice that it's dependent on lamination thickness. You can see the column headings there are for various lamination thicknesses. And you can also see that there is a difference between ACHAR, or the calculated char depth, and A effective, the effective char depth. Again, effective char depth is what's used for structural fire calculations. So using the CLT char depth model, a thickness of CLT that's equal to the effective char depth is subtracted from the exposed surface, just like the procedure that's used for other wood members. However, unlike for other wood members, the cross-section of CLT has a distinctive orthogonally oriented layer layup. So this needs to be accounted for in the design. And of course, since it's a mechanics-based design, you have to account for the fact that those layers are orthogonally oriented. And you can find more detail on how to do that in TR10. Specifically, example 4.6 actually gives an example from start to finish on how to perform that calculation for CLT. But then there's also a simplified method for design of CLT, and that's outlined here on this slide. So, for example, if you had a 5-layer CLT having a 1 3/8 inch thick lamination thickness, the fire design could conservatively be based on design properties for a 3-layer CLT made of the same lamination types, as long as the remaining effective depth is greater than or equal to the combined depth of the 3 laminations. So in this case here, it would be 4 1/8 inch if you had a 3-layer CLT made up of 1 3/8 inch lamination thicknesses. So This would work for this in this particular example, it would work for a 1 hour fire resistance rating, but it would not work for 1.5 or 2 hour fire resistance ratings. I'm sorry that it keeps advancing automatically on me, and I hate that. I need to take that off of this presentation. So let's see. So the calculated fire resistance of timber decks, including NLT, nail laminated timber, can be calculated using section 3.3 of the FDS as well. And the provisions for NLT are in section 3.3.3.1 of the FDS. And these apply to tongue and groove or mechanically laminated tongue and groove planks or mechanically laminated dimension lumber that's set on edge and nailed to the adjacent pieces. So that's basically NLT. I don't know if any of you have dealt with NLT, but those are the provisions in the FDS that would deal with that. And under this method, you basically analyze or you calculate the char penetration that occurs between budding laminations. And can you see my cursor when can you see when I do that on the screen? Okay. So you can see here that there's char penetration occurring at the interface, the budding edges between the members in the NLT here. And that's assumed to progress to a depth of twice the calculated HR or 2HR. And you analyze the section properties of the or the remaining section properties of the NLT based on that. So then there's also there's an alternative method, which is that's the method that's been recognized in the NDS for several editions now, which it uses if you have tongue and groove laminations, for the NLT, then you basically just assume that there's no exposure on the edges, or I'm sorry, there's 1/3 of the exposure, 1/3 HR exposure on the edges, and the full exposure on the bottom edge, on the bottom surface. And then if it's butt jointed, like most NLT is, then you would assume full exposure on the edges and full exposure on the bottom. So clearly, this new approach that uses the 2HR char penetration between the laminations is it's a better approach. It gives a better answer, less conservative answer, less overly conservative answer for most lamination thicknesses. Basically anything that's about 2x4 or greater for your NLT laminations, it gives a more refined answer, more optimized answer. And then there are also exceptions to these provisions, and that's what I just mentioned. So these are the 1/3, effective char rate, and on the edges, and then the full char depth on the bottom edge. So that's like what you have in the NDS. But again, I would recommend sharpening the pencil. You get a more refined answer for using the normal FDS provisions rather than the exceptions. All right, so let's talk about glulam a little bit. For glulam members, they typically have stronger laminations at the top and bottom when compared to the laminations that are closer to the neutral axis. So because of this, additional tension laminations are required in order to replace the interior core laminations so that the extreme fiber remaining on the reduced section after it's been exposed to fire for a little while still has adequate strength. And this detailing provision requires some communication and coordination between those who are doing the fire resistance design and those who are responsible for the structural design, if those are different individuals. So because it has to be ordered that way, has to be specified that way in the plans. And I was going to mention that the FDS contains provisions that pretty much the same from a practical standpoint. You get the same answer as the provisions for glulam design in the NDS, but the FDS is greatly expanded. It provides a lot more detail, and additional illustrations are provided in the FDS that are not in the NDS, along with a lot of additional provisions. All right. So far, I've only been talking about the calculations that are used for calculating fire resistance of exposed wood members, but you know, and so using this mechanics-based method, there are two main factors that go into determining the fire resistance of an exposed wood member, and one of them is, of course, cross-sectional dimensions. As the greater the cross-sectional dimensions, generally the greater the fire resistance rating. And then secondly, the other one is the load ratio, or the ratio of ASD to, or the actual load applied to the ASD design load. And the fire resistance rating would actually be increased. The fire resistance rating of a member would be greater if the actual load applied is less than 100% of allowable stress design. And the reason for that is, of course, because if there's less load applied to the member, say it's less than 100% of the allowable stress design value, then less section is required in order to carry that load. So it allows for a greater amount of time, or more section loss, because think of it this way: time is equated to section loss when you're talking about fire resistance duration or fire endurance. So remember that when it comes to the new fire resistance ratings for the new mass timber construction types, you're allowed to combine. In fact, sometimes you have to combine the calculated fire resistance rating of the wood member itself with the fire resistance rating of any non-combustible protection that may be applied to the surface of the wood. And this is a very important point, because it's actually one of the characteristics that distinguishes fire design of wood from that of other construction materials. For wood, you can rely on a calculated amount of inherent fire resistance of the member itself. And then, if necessary, you can add to that any additional protection, the time associated with any additional protection that's added to it, either non-combustible protection or combustible protection, as the case may be, like additional wood cover.
We got about 5 more minutes here, Jason.
Okay, I may not be able to go into the fourth section then. Okay, that went fast. Sorry. All right, as I mentioned, the FDS section 3.3 provides guidance on how to determine the amount of protection time that's provided by additional wood cover and wood membranes. And this graph shows these are the equations that are in section 3.4. And you can see here in this graph, the blue line shows the time that you would get related to various thicknesses of additional wood cover, and then the orange line is wood membranes. The difference is that wood cover is in direct contact with the protected wood member, whereas wood membranes are not. So, like a wood membrane would be like a plywood, a membrane of plywood applied to a wall, a stud wall, for example. It's not in direct contact, at least not full contact with a surface. Part of that is exposed, or it's open on the backside. All right, and then FDS table 3421 quantifies the protection time that's provided by Type X gypsum panels, and these are the same values that you see in the in the IBC. So you get 30 minutes of protection time from 1/2 inch Type X, and then 40 minutes of protection time from 5/8 inch Type X. And these are all based on empirical testing, of course. And then FDS table 3431 quantifies protection times provided by different types of insulation, specifically mineral wool bat and fiberglass insulation. And you can see that there's a big difference between the value that you get for fiberglass, insulation versus for mineral wool insulation. And the reason is because the relative melting points of those insulation types. By mineral wool, I'm talking like stone wool, whereas fiberglass, the glass melts at a lower temperature. But you can rely on, as you can see, you can rely on at least some contribution from the insulation to the overall fire resistance rating of the assembly. All right, well, I don't know. Maybe I won't get into connections here. How much? I only have probably like 2 or 3 minutes left, right?
Yeah, I
Yeah,
mean, if
it'd
you
be good
just,
to start. Oh,
Okay.
go
go
ahead.
ahead, Sam.
Well, let me just at least point out that there's a fundamental difference between type 4, traditional type 4 construction, which is now type 4 HT, and types 4 A, B, and C construction. And I mentioned that fundamental difference earlier, that is that types 4 A, B, and C require fire resistance ratings for most of the building elements. And then that translates into it makes a big difference when it comes to the connections because connections between building elements are required to they're required to have the same at least or no less than the fire resistance rating that's required of the connected members. And so therefore, in order to protect or in order to ensure that those connections have a minimum fire resistance rating that meets that requirement, you actually have to protect the connections. And that's where these two IBC sections come into play, 704.2 and 704.3, which require that you protect the connections for the minimum fire resistance rating, period. And then 2304.10.1 of the IBC, it provides two different ways that you can demonstrate that minimum fire resistance rating of the connections. One is by testing, and then the other one is by engineering analysis. And that the engineering analysis approach is the one that is addressed in the connection protection provisions of the FDS. So that basically specifies that you can't exceed a temperature rise threshold of 250 degrees at the interface between the protection and the connection itself. So anyway, yeah, the provisions of section 3.10 of the FDS kind of go through, they go through how that can be accomplished, how you can demonstrate that you meet that temperature rise threshold, that you do not exceed that temperature rise threshold at the interface. Anyway, I'm sorry. I knew we would run short on time because, like I said, this was designed to be a 1 hour presentation. But if you have any questions about any of that, including connection protection, I'll be happy to answer that.
And real quick before we do get into the question, sorry, Sandra, just to reiterate again to everybody, the full presentation is out there on our website, a recorded version of that. So if anybody's interested and you can't find it out there, feel free to reach out and I can send you in the right spot if you do want to watch the last little part there about the connections.
Well, Jason, thank you so much for that presentation. I think that was a lot of excellent detail, and I am going to need like somebody to do a Schoolhouse Rocks version of that for me to get it. But really good, and I'm sure very relevant for many people on this call. So thank you, and thank you, Ed, for getting Jason mobilized to do this.